Process of analyzing designs consists of the same basic steps, regardless of the type of analysis or model. Although all of the following steps must be completed, many of them can be done in any order desired by the user. First, a study is created. Multiple studies can be created for a single model if needed. A material is applied to the model, which contains the physical information such as the yield strength of the model. Fixtures are applied to the runner, which represent the way the physical product is held. Loads are applied to the model to represent the forces that cause a part of deform. A mesh breaks down the model into a collection of small, simple elements. This allows to solve the find values, such as the stress and displacement at each point where the elements join together. Once all the previous steps are complete, the study can be run to calculate the results. Finally, the results are displayed in graphical plots according to the result type, such as stress or displacement. In this lesson, I will fix the two bolts holes of this bracket in place and apply a 500 Newton of force to the counter board face. Using simulation tools, I will find points with the highest stress along with the maximum displacement for the part. The bracket shown here will be used to run the simulation study, which will give us the stresses and displacements that results from the forces and fixtures applied to it. The fixture will be added to the inner cylindrical faces of the two bolts holes, simulating the bracket being fixed in place using two bolts. Once the fixtures are applied, an external force of 500 Newton will be applied, normal to this counter board first face of the vertical cap. To begin creating the simulation study, I will simply activate the simulation add-in. To do this, click on the drop down arrow next to the option icon and select add-ins. And when the dialog box appears, check the box next to Solidworks simulation as well as the startup checkbox is desired, and then click OK button. Now I will activate the simulation. To begin a simulation study for this model, select new study. The property manager prompts me to create a new study, which I will name stress analysis. I will make sure it's set to be a static study type since load does not vary with time and material are linear material. Upon clicking the green check, the study is created. You can see here that the new simulation study has a number of items to be specified in order to solve the model. These items can be defined step by step, or they can be done in any type, providing you the flexibility to define them as you want. There is no specific workflow for the simulation tree. However, some of these items must be completed for the solver to run. To begin defining aspects of the simulation, I need to access the simulation tools. This can be done by the right click on any of the items in the simulation tree, or by selecting the simulation drop down menu at the top, or by enabling any of the tools from the simulation command manager. A common first step in a simulation is setting the material for the part. As mentioned before, this does not have to be the first step. However, in this exercise, I will be following the order found in the simulation tree. I will right click on part and then select apply edit material. Here I like to mention that if a material had already been defined for the part in the design process, that material would be pulled into the simulation study automatically, eliminating this step. However, a simulation study adds flexibility by allowing you to select any material for the study without changing the material defined in the 3D CAD model. You have access to a rich material library for your simulations. For this study, I will select the material aluminum 106 alloy, and you can see below that some of the material properties are shown in red and blue. The red properties are required in order to run the static simulation, and the blue properties are optional. One of these properties, the material yield strength, is one of the most important properties, which will come out later when I will review the results. With the material selected, I will click apply and close the dialog box. Now you can see the material applied to the part shown in presentation in the tree, including a green check show on the part icon, which indicates that this study item is complete. For this model, there are no connections needed since this is a single part, and there are no part-to-part interaction present in the model. Specified connection will come in later lessons when examining interaction between multiple parts. In the next video, I will walk through the remainder of the setup item in the simulation tree to fixtures applied to the part, the external loads applied to the part, and the mesh that breaks apart in smaller solvable pieces called elements Now that the material is defined for the simulation study, I can begin defining fixtures in the model. Fixtures define ground interactions, which defines parts that are not explicitly modeled in the simulation study. As mentioned earlier, the fixtures will be applied to the two bolt holes in the base of the bracket. This time, instead of accessing the simulation tools from the tree, I will go ahead and click on the drop down arrow underneath Fixture Advisor and select the option Fix Geometry. This brings up the Fixture Property Manager. I will make sure that the Fix Geometry option is selected as a fixture type. And you can see a graphic visualization how the rest of the part moves relative to the fixed face. The fixed inner face of the cylinder, I can click on it, as well as the inner face on the right. And if I zoom into the hole I just selected, you can see a green arrows pointing in all direction. Fixed faces appear with green arrows in the graphic area, and the number of arrows indicates how many directions are fixed. Now I'll click on the green check to complete adding fixtures, and you can see the fixtures added in the simulation tree. The next step is to add the external load to the model. This time I'll go to the simulation drop down menu and however load fixture. Here you can see a number of loads that can be applied to the model, including some prescribed displacement as well. For this study I'll choose the option force. The force torque property manager appears, and I will select the force as my type. I will apply the force to the face of the counterbore hole. I'll make sure this is a normal force and set it to 500 Newton. Notice that the arrow in the graphic area are shown in purple, which indicates a force. They are also pointing in the direction of the force, which is normal to the face. Now I will click the green check to finish adding the force. The simulation tree updates the force is listed under external loads. The process of meshing takes model geometry and turns into a collection of small, simple shapes that the software can use to calculate the stresses and strains. Each of these small simple shapes is referred to as an element, and the combination of all the elements is known as the mesh. To apply the mesh to the model, I will right click on the mesh in the tree and then select Create Mesh from the menu. The mesh density can be adjusted here with a sliding scale ranging from coarse to fine. If the density is set to coarse, there will be less element created in the mesh, which often allows the simulation to process quicker but is less accurate. However, if the mesh is set to fine, more elements are generated in the model, which allows the simulation to produce much more accurate results. However, it takes much longer to solve the study. I'll go ahead and reset the slider by clicking the reset button, which places in the center of the scale. Under the mesh parameters, there are also three meshing algorithms that can be used: blended curvature based, and standard mesh, which calculate the mesh for the model. For this example, I will select curvature based, which creates a mesh with the variable element size. This allows for a more accurate resolution of small feature in the geometry. Now, when I click the green check, you can see the mesh applied for the entire model, which has also broken the model down into collection of elements. This completes all of the items needed to run the simulation study. Now all of necessary setup information is complete for this model. I can go ahead and run the study. I'll click the Run this study button in the command manager, and the solver runs. Once a solver is complete, a results folder appears in the simulation tree listing various results, and the one misses stress plot is automatically shown. A color gradient appears overlaid on the model, which corresponds to the key shown to the right. Each color indicates the stress found at the point. Stress is the internal resistance of the part to the loads applied to it. If I take it a closer look, I can see the stress connection developed at the base corners of the tab, indicated by the yellow and red coloration. The bolt holes also indicate region of height stress. In the key on the right, notice the red arrow pointing to the orange region of the scale. This corresponds in this yield strength of the part. The yield strength is the highest stress a part can withstand before the part can return back to its original shape. This means that the regions in the model that are in red will permanently deform and will not return back to their original shape, which can often be considered a mechanical failure. Now I will take a look at the displacement plot. This plot shows how far the part moves from its original shape. However, the deformed shape shown in the graphic area is not realistic representation of the part after the load is applied. This displacement plot is exactly rated by the scaled amount. As indicated in the top left corner, the displacement of the part can be eliminated by the right clicking on the plot tree and then selecting animate. This shows how the part moves when experiencing the external loads, which is also exaggerated by the deformation scale. In reality, the maximum displacement for the part is 0.068 millimeters, which is much smaller than what is being shown graphically. Thus complete the entire simulation study, including showing both the stress plots and the displacement plot for the model.